So my name is Amir Hossein Sadegh-Manesh. I am currently working in group of Matthew England at Coventry University, and our work is supported by GeoCat project. So in this talk, I will first talk about a question in population dynamics, and will tell you how it is related to algebraic geometry, discussing the former existing algorithm and their limits, and then introducing a new algorithm to solve the question, and we have some closing remarks. So the most well-known population model is logistic growth that you might have seen in your calculus courses. So you have a population which I denote its size by capital N, and n dot means derivative of n with respect to time. So what happens is that at the beginning your population starts growing, but they cannot grow to infinity because there is a limitation of the resource or food, or there is a limitation of the volume and size of the environment. So there is a maximum capacity that the environment can support, and as the population become closer to that value, the speed of their growth gets reduced until they eventually reach that carrying capacity. So there are two steady states. By steady state, we mean the population is not changing, is stable, which means the derivative is zero. So there are two steady states. One is zero extinction. If you start with zero population, you remain zero until the end. If you start with non-zero population, you end up with carrying capacity. A more fun model is a model with a strong Allee effect. So in this case, it's not only competition for the resources, but there is also cooperativity. Let's say you have a fish that releases some chemical from his body to the water, which makes the environment safer for him, immune to some disease. If you have very few number of that fish in the water tank, then the amount of that chemical is also very little, so the water is not very safe for them. They start dying out. But if you have more than a threshold, which we call it Allee threshold, of that fish, then the amount of that chemical is enough in the water and they can survive. So here you have three steady state: extinction and carrying capacity and Allee threshold, which is the unstable one. And the equation is like this. You can normalize the equation so that the carrying capacity is 1, and then you have only one parameter b, which is the Allee threshold. So when you have one population, it's not much fun because you can see every data and information you need from this diagram. It will be more fun if you have more number of populations. Let's say you have n patch, and by patch I mean different geographical region, or it can be different countries in an epidemiological context like the COVID system. So here I'm showing 3 patches, and we have 3 populations, all of them showing Allee effect with the same parameter b, and these patches are connected. I consider the fully connected digraph for simplicity, and I considered same dispersal rate or strength of connectivity, again for make things simpler. And then the equation is like this. You have n differential equation of this form, and now things are more interesting. So it was studied before, and it was shown that for small value of a, the system behaves like n independent populations. So you have 3 to power n steady states, and when a is large enough, these all patches together behave as one larger patch, and you have 3 steady states. But there are questions left. What about the intermediate values of a? And also, is it the case that the number of steady states for a fixed value of the Allee threshold by varying the dispersal rate is monotonically decreasing from 3 to power n to 3. Is that the case? So these were the questions that I had to study 1 year ago when I was at Szeged University in group of Gerger Roche. We started studying it by algebraic geometry. There is one tool, computational tool in algebraic geometry called Cylindrical Algebraic Decomposition that can answer this question deterministically. Let's explain what this method is in a simple example before attempting to our main question. So here you have one equation with one variable x and two parameters b and c. And you are interested to know for which values of these parameters, how many solutions you have. So this algorithm, the first step is to compute discriminant variety using elimination theory via Gröbner basis. What it does is it gives you a new set of polynomials free of the variables only involving the parameters. Here in this case only one polynomial b squared minus 4c, which its solution set is plotted here. It's a curve like this. Then it decomposes, we use OpenCAD, it decomposes the parameter space with respect to this curve to finitely many connected open sets, here in this case 4 cells. And then there is a fact that the number of solutions of the system for 2 points from the same cell is the same. So if I pick up one sample point from each of these 4 cells and try it in the original system and count the number of solutions, I know the number of solutions everywhere. And the result, the final output is that here you have 2 real solutions and here you have 0 real solutions. So this is the algorithm. It is already implemented in Maple in a package called RootFinding Parametric. So we said, let's try it first. So by Maple star, I mean Maple on our laptop, and with CAD star, I mean OpenCAD with respect to discriminant variety implemented in RootFinding package. So for two patch, our computer could finish the computation, and you see that it starts for fixed value of b. When you start with a small value of a, you have 9 steady states. Then when you increase it becomes 5, then it becomes 3. Okay, that was good. But unfortunately for 3 patches, the computation could not finish. Okay? This algorithm has double exponential complexity, and what happened for our case was that the memory of computer got full. So after some point, there was nothing more happening. Okay, so did we give up? Well, no. We said that with both parameters a and b being free, the computation could not finish. But let's fix value of b, and then only letting a to be free. Then Maple could finish the computation for this algorithm, and we could get the one-dimensional CAD. So what we did was, well, coming up with a numeric algorithm. The first stage of the algorithm is trivial. You pick up several number of values for b, and you get the one-dimensional CADs that it's possible for computer to compute. And the result of those one-dimensional CADs are the intersection of the boundaries between different regions with different number of solutions with the horizontal lines, as you can see. So you get a rough feeling of what shape those boundaries could have. And then the second stage of the algorithm does some numeric search to find where the behavior of these boundaries change. And the result was it found 2 places. One place a crossing happens, another place you have an interesting curve with sharp points somewhere. The final output of the algorithm was this picture at the left side, which in a tiny region here, we zoomed it, enlarged it. In the right side, you see that interesting curve. So what it says, it says there are some choices of values of B that when you increase A, the number of steady states start with 3 to the power 3, 27, decrease to 21, then decrease to 15, decrease to 9, but temporarily increase to 15 and then goes back to 5 and then 3. So a discovery was that the conjecture was not true, it can temporarily increase, and here is one example. And the result is guaranteed by 7 digits of accuracy. If you want more, you have to increase the digits of accuracy and then run the algorithm again. So that was what I had done previous year in group of Gergely Roche. But this year in Coventry we said, let's see why the deterministic algorithm could not finish the algorithm. So if you remember, it had 2 stages. First computing the discriminant variety and then the open CAD with respect to that. So we said that let's try the first stage alone using Gröbner basis and elimination theory. Well, we found that the memory of computer got full and the first stage alone could not finish. So the first idea came to our mind was to let's get rid of the first stage, get rid of Gröbner basis. So we use an alternative, which is the projection operator of the CAD. Let's skip the details. So we compute a new set of, like say, curves or polynomials that their solution set contains the discriminant variety. It is more than that, but it contains the discriminant variety and is free of Gröbner basis. And that alternative, so Gröbner basis is known to be worse doubly exponential. And projection operator of CAD is also doubly exponential, but using equational constraints, we can make the projection operator to be singly exponential. So that's a good trick that we use. So yeah, we replace the first stage with something free of Gröbner basis and singly exponential. And the second step, we kept the open CAD the same. So we didn't change anything for the second stage of the algorithm. We run an algorithm on the example that we had, this 3-patch. As you can see, we have more curves, but they contain the boundaries of the regions. And for that small region that we zoomed previously, you can see we got 2 more curves. But anyway, when we pick up the sample points from the cells with respect to this new curve and we substitute back, we get the same result. The red colors means 15 steady states, and the orange color means 9 steady states. So it shows that what we found previous year numerically was exactly everything. Now, okay, so what is new? The new algorithm is free of Gröbner basis, so it's and is singly exponential, is better than the previous deterministic algorithm. It is also free of numeric approximation, so it is better than the previous year numeric approach. And some of you may ask that now that we have this deterministic thing that could do the computation for 3-patch, is that numeric approach of previous year useful anymore? Well, the answer is yes, it is still useful. So remember, with the previous deterministic approach, we could go up to only 2-patch, and then for 3-patch we had to equip this numeric on that previous deterministic algorithm and get the result. Now the new deterministic algorithm, we haven't checked how far we can go yet, but when it goes up to some level and then it cannot go further, you can equip this previous year numeric algorithm on top of this one, using this one for the one-dimensional CADs, and then going for larger examples. So both this year and previous year algorithms have their own good aspects. Okay. And here are the references. Thank you for listening.